Okay, I see Hussein is in the chat. Let's see if he can figure out how to join us. Okay.
Hello.
Hey, Aaron.
Hey. I'm here to say hello before you get started.
Oh, perfect. I think I've got this good. I see Hussein's here, but I don't know if he can join. Oh, there we go.
Nice.
Yay!
Perfect.
Yay, we're all here.
Good.
This is amazing. Awesome. I really have to give a big thank you before we get started to Hussein and Alex who have agreed to lead this session. Yeah, this session all came from this session really was inspired by a comment from a current graduate student who said, I really want to learn how to master Python visualizations. And we were so happy that Hussein and Alex were willing to step in and do an hour session to get people up to speed in Python and Python visualizations that they asked for. So Hussein is a graduate student with the Whole Brain Modeling Group at the Crumble Center for Neuroinformatics at CAMH, and Alex is a MRI specialist or MRI specialist, I think is the title.
I have like
imaging
I always have a different title. I don't
know. Working with our neuroinformatics platform at the Crumble Center for Neuroinformatics in the operations team, and we're super happy that they're willing to come teach and lead this workshop today. So without further ado, I'll let you guys take over.
Okay. Before you go, I just have one question.
Yes.
How do I do a poll? I know.
Oh, I think I need to do the poll for you, I realized, but I can. I have the power.
Oh, okay. I'd just like a quick poll then for people's experience with Matplotlib or visualizing in Python.
Cool.
Because I just want to know, because we have a couple things this workshop, but it's only an hour, so I want to know where I should really put the focus on, if I should gloss over some of the more basic stuff, or if I should really dig in there. So yeah, everybody in the chat, answer the poll once it gets made.
Oh, that was supposed to be Python. I apologize for my quick typing. Fishcon. Fishcon is a new language which will be invented right after this.
I have intermediate experience with it.
Yes, an intermediate.
Okay, so we've got a mix. We're split down the middle. So I guess I'll then I also encourage you just really put questions in the chat and I'll try to answer them live if stuff's not clear or if you notice something you are more interested in it. But it looks like the majority is none. So we're going to start from the basics. The way this is going to work is we've kind of got two parts to this. First, we're just going to go over plotting just kind of basic data, kind of normal data, quote unquote. And then the second half, Hussein is going to take over and he's going to show you how to plot. I mean, this is BrainHack, so he'll show you how to do stuff with actual brain data. So we have this notebook here. I'm wondering, can we share files on this or no? I
What
don't know how to do that.
would you like to share?
I'm just wondering if we should share the notebook with people if they want to follow
Yeah.
along in the notebook.
Okay. I'll send over the link to the GitHub repo.
Yeah, so we have this on GitHub. Then you can follow on directly with the notebook. You're also free just to open your own Jupyter notebook if you want. I'm running this in Google Colab because one of the HTML5 visualizations worked better in here. But you can really run it on whatever you want. If you're, I'm hoping you're at least familiar with Jupyter notebooks. If not, maybe put some questions and maybe Hussein can try and help you set it up while I start. But I'm just going to get started. So Matplotlib is kind of the workhorse of doing visualizations in Python. It's based off of the MATLAB plotting API, if any of you are familiar with that. So that has its advantages. If you're coming from MATLAB, it kind of has an intuitive similar feel. It's also, though, it's not quite as nice as plotting, for example, in R. It can be a bit cumbersome with the API. So hopefully by the end of today, you'll be able to at least be confident enough to dip your toes into that API. Another big advantage of Matplotlib is it has all these other packages that are kind of built around it or on it and to work with it. So we're going to be touching on a number of them today, but obviously NumPy, if you're familiar with Python, works really great with Matplotlib. Pandas has a lot of built-in support with Matplotlib as well. And then these kind of better plotting packages like Seaborn and Plotly, which I believe we'll be talking about Seaborn today, that extend Matplotlib, and then they also work themselves with NumPy and Pandas to make plotting as painless as possible, because really we just want to get pretty graphs with as few lines of code. So well, here's an example you set up. If you haven't installed Matplotlib into your Python environment, you can do that with a conda install or a pip install. But I'm assuming if you're working with conda, the basic package that Matplotlib comes with that. So hopefully you'll have everything. So let's just get started. So the very first thing we got to do, as we always do in Python, is import all our libraries. I'm going to actually make this bigger. Can I? Yeah. That look better for everybody? Yeah, there we go. So obviously we're just going to import our libraries. The first ones we'll be using to start are mostly NumPy and Matplotlib. So you import them as NumPy as NP and Matplotlib.pyplot to get the plotting as PLT. These are just kind of conventions everyone uses. You can import them as whatever you want, but this will make your code more readable for others. And we're just going to make our first really simple graph. So we use this NumPy command just to generate a line of values, a linear values, and then we're just going to make some y values with it. And then this is going to be the meat and potatoes of our presentation, the plot.plot command. And you pass in the first data you pass in is going to be the values for the x-axis, and the second one are going to be the values for the y-axis. I'm going to run this, execute this box, and then I'll go into what the other stuff is doing. But we just want to see this work. So this is our first, ta-da, we didn't do plot.show for all of these. So this is another thing. If you don't call plot.show, in the notebook it will still pop up, but so I'm adding these on the fly. So the main thing you do is when you call plot.plot, this tells Matplotlib, grab a figure. If there's no figure, make a new figure, and then plot on it. And then if you call plot.show, it shows the figure. If you're running in a notebook, you don't have to call it to see it. But if you were running it like in a local Python environment, it won't pop up on your screen unless you call plot.show. So I just want to show these. So this was the very first figure we did, just this X and Y where we just made a space. And ta-da, it's just really simple. It's got an X-axis, a Y-axis. It auto does the ticks based on the data you put in. And the default color is usually blue. Then I'm just going to go to the second command here. So this is where we're starting to add things to our graph, right? Because obviously, if all the graphs look like this, that would not be very fun. So the way you control how your graphs are appearing are with all the keywords you put in. So these ones we've used C for color. And there's a number, I think there's about 8 basic colors that can use that are, you can just pass single letters to get, but you could also pass, full words. That will work as well. And there's more colors for that. Line style, we use the dash line style. Line style, similarly, there's about 5 reserved strings. For example, I think if you just do this, it's just a normal, completely filled line. This gives a dash line. This gives a dotted line. And line width is just out the thickness of your line. And then on our third graph, we use the marker keyword. So this is actually controlling the actual plot points, not the line, but the actual data points you have on there. And then similarly, you can control their size. So this just gives us 3 different plots, as I said. Our first one where we did nothing, this is what Matplotlib will put out. Our one where we decided to do a dash line with red, and then our one where we decided to do the markers with stars, though there's a lot of data points, so you can't quite see them. This is another thing. So each one of these I called plot a new time in the plot.show. And each time I'm calling plot and then plot.show, it will show that figure. And then when I call plot again, it's going to call another figure. But you can obviously, a lot of times you need to plot more data on a figure than just a single set of values. So in this example, we're going to plot multiple data points. So we're doing the same thing here. Here we're just using NumPy to once again make some dummy data, and we're using NumPy sine just to make sine waves. And then I'm introducing here the label keyword. So this labels the line that you've plotted so that later when you call the plot.legend, it will automatically put those values in for you. So I'm just going to run this now, and you could already see the image because it was in the notebook ahead of time. But as you can see, we got 2 lines here. So we just called plot twice without calling show or plot. Oh, well, I called plot.plot instead of plot.show. But it's one figure. But every call you make to plot will just be calling the same figure. In the background, it's running a command to be like, grab the current figure, the most recent figure, and just plot on that. So if you haven't done anything fancy, if you're just plotting stuff, you can just keep on adding data to figures. So just showing, kind of to reiterate, if you call plot.show in between each of these, then you'll get 2 separate plots. Whereas if you get rid of this, they'll be plotted on the same figure. If I just delete that and run this, now they're on the same figure. This is just more of the same. I think we had some redundancy. So I'm just going to skip this part, but now I'm going to go really into the details of how we're going to customize our figures. So I mentioned a few keyword arguments, and that's really how you're going to control how your figures look. So in the Matplotlib documentation, there's like 1,000 keyword figures. You can really control everything. But most of them you're probably never going to touch. So here I've highlighted a few that, or at least the ones I use most frequently for the plot command. So this is alpha. This is how you can control the transparency of your appearance. So you could imagine you want to plot, a background line, but then you want to plot a line on the foreground, but you want it to be slightly see-through. So this one, you just pass a float between 0 and 1. 0 would be completely see-through. 1 is completely opaque. And it will allow you to kind of manipulate that. We'll see that in action. C, or color, as we've seen, just controls the line color. As I said, there's some reserved single letter colors, like R for red, B is blue, G is green, K is black, but you can also put in full words. The label, as we talked about, was for hitting the legend that comes up. And then we've seen this line style and line width as well, and the marker. So these are the ones that just really come up a lot. They really help you to at least kind of differentiate things on your graph too. But then there's also the fact that we don't just want to control the actual plot. We want to control the axes and the appearance of the rest of the figure. So the way you do this is using, I've put out a bunch of commands here, and I'm going to demonstrate them in a moment, but I'll explain them a bit. So we call matplotlib, and there's commands like xlabel and xscale and xlim. And for each x value, there's also an associated y one, so a y label, a y scale. And these do mostly what you'd expect them to do. So the x label puts a label on your x-axis. So you want to name it time or something. The x scale controls what scale you want on there. So normally matplotlib defaults to linear, but you can obviously make log graphs, you can make logic plots. You can do, I think, there's one more I can't remember. Xlim is how you control the limits of your x-axis. So say you don't want your graph to just be plotted from the exact start to end of your data. You want more of a buffer, or you want to make it look really small for some presentation purposes. Xticks is how you control both the location of the ticks on the axis, and you can pass labels to it as well. So if you want to give custom labels. Plot.title, I think that's pretty straightforward. Plot.grid, we've used a few times. It's how you get the nice grid lines. Just makes it look a bit easier to read sometimes. And then plot.legend shows the legend. So this example is really going to demonstrate a bunch of that. So we're just generating a ton of sine data and cosines. It doesn't really matter what it is, though. It's mostly just dummy data that we're going to use. And here I'm going to show you something I do that you'll do more as you become more comfortable with matplotlib. I call the figure directly. So I use the plot.figure command to actually return the figure object so that later I can do manipulations on it. Additionally, it allows me to control the actual size of the figure that's displayed. So you call the fig size keyword and you pass it a tuple. And I believe the first one is the length of the figure and the second one is the height, though we'll see in a moment. Maybe I'm wrong. I always mess it up. I usually have to redo the figure. But this allows you to get more, instead of just getting a default size, always if you want, a really long finger, or, you just can get whatever size you need for your purposes. And now we're going to use all these keywords I talked about. So as I said, the line style, here I've got a dashed line, a dotted line. I'm going to plot different colors. I'm controlling the line width. I'm just changing the line width to random ones. I just want to show you that they're different. I'm making them transparent so you'll see what that looks like. And then I'm giving them a label. And this is going to give me a moment to mention something really important. Matplotlib supports LaTeX in the plot titles, in the labels, and in the labels for your axis ticks as well. So you can, as long as you do it in the LaTeX with the, going into math mode with the $sign, you can put in LaTeX math expressions. So this really allows you to guess up, especially for scientific purposes, your graphs. So I've just labeled these Y1, Y2. I'm giving it a title, a stupid title. And here I'm using other commands like font size. That's the keyword that you can use anytime using words. That will allow you to control the font size. Similarly, font name, you can personalize the name, though you might want to make sure you have those fonts on your system. And then here I'm just showing I'm using the X label, Y label. And then for this graph, I'm controlling the ticks. So the way I do the ticks is I pass where I want the ticks to be numerically. And then I pass the labels, which are the strings that I want for each. And the only thing that's different with this from the other labels is you have to append an R to the strings for X ticks and Y ticks for some reason. Otherwise, it will try and interpret the same string before it passes it to LaTeX. This is what I mean with the matplotlib being a bit confusing sometimes. Anywho, I'll show you what this graph looks like. So now we've managed to plot two sets of data. We've controlled our title. We've controlled the size and the styling, the color. We have a legend. We have these nice LaTeX ticks where we want them. And I'll show you, for example, what the alpha does. Like I'll change one of the alphas to just 1. And I'll do it really dramatically. It's 0.3. And then you see this one's 0.3. You can barely see it, but this one's nice and bold. So that's how this is how you start to really make your data presentable in a way that's not just the default. This is just a command. If you want to see what fonts are on your system, you can run something like this. It's not really too important, but it will tell you which ones at least Python can see. So now I'm just going to show you how to do subplots. So we've been plotting stuff up until now. We've been plotting stuff all onto the same figure. But obviously also you often want things in separate plots, which you can do by just using what we did before with the plot.show each time. But what if you just want a single PNG, right? You just want one figure. So this is where the subplots come in to play. So instead of using the plot.plot command, we use the plot.subplots. And then we tell it how many subplots we want. So the first number is how many rows you're going to have. And the second number is how many columns, because you're essentially making an n by m grid where you can then plot on each of these different points in the grid. So I'm just doing a 3 by 1 here. And you can control the figure size as is. But when you call subplots, as I said before, you get the figure. Ooh, you get the figure. We might be having a fire alarm in here. I'm just a moment. Could you take over for a moment, Hussein? Do you think?
Sure, absolutely.
I think we're just having a fire alarm.
No worries. I think you're almost done with your section, by the way.
Yeah, I'm just about
if there's
done.
like an emergency or something, that's, you know.
Here, yeah, take over for a moment. I'll see if this is just a drill.
Why don't you mute your mic, because, yeah. Okay. And I'll start sharing. Okay, so I've just started sharing one of my own windows here. Okay. Maybe skip down a bit. Where did we leave off? All right, subplots. There we go. Okay, so Alex was, yeah. Never know what's going to happen here at BrainHack. Okay, so Alex was just discussing subplots, essentially plotting multiple plots on a figure. IPy notebook or Jupyter notebook, which is what I'm using right now, in contrast to Alex using Colab. Both of them let you use subplots by letting you just show multiple figures being produced at the same time. And this is just insanely helpful, obviously, for publication, in which figures will not just be a single graph or a single plot, but a collection of them. A few examples shown here with, okay, so just simply using the subplot commands, 3-1, indicating 3 rows and 1 column of figures and giving it a certain figure size. So the figure sizes, by the way, that also differs between what you're using to output your figures, whether you're just printing them out in Python and and running them from the command line versus how they're displaying on Jupyter Notebook, which is what I'm showing here. I'm not going to run this right now because I mean it's already run and the figures are displayed right there. But and also I would have to start over from the beginning, I think. I would have to start over from the beginning before running it. But there are some other ways within Jupyter Notebook to change the sizes of the figures as well. So just be mindful of that. That fig size is not the only option you have. So given the data we have with a certain lin space, so a space of values looks like Alex had set this to go from minus pi over 2, so minus 1/2 times pi, to 3/4 times pi with 100 steps. So that gives you a range of x values with 3 different functions, a cosine and 2 sine functions. We can just plot them. So if we have some sort of arbitrary signal system, and maybe this is like an input type of data. Maybe this is like an input current that's varying over time. This is voltage. This is voltage, excuse me. Maybe this is like an input voltage that's varying over time from some sort of external current source or external electrical or electric potential source, either in a neuron stimulation or a similar system. And yeah, so the rest of the code is pretty self-explanatory. Making note, so just taking note that we use three different axes, or we use three different values in this axis variable, which is set up here. So the subplot function returns two different variables: fig, or the figure itself, which you can use a super title and show with the legend, and axes right here. Axis gives you control over each specific subplot, and by simply adding a variable, or by simply looking at each element within axis, you can plot, set the color, add a grid. So, or sorry, you use the grid and then use color equals white to set the color for the grid lines. So that's being shown on each graph, the actual grid lines, making it easier to parse out what the numbers are, and the Y label as well. So yeah, again, the rest of the variables are pretty self-explanatory. I'm not going to spoon feed them to you because you can just read what they are. And yeah, interestingly enough, this also just gives you this also gives you a lot more control. This also gives you a lot more control in producing either multiple figures at the same time or multiple plots on the same figure in a way that's very, very simple, concise, and neat, and just very, very straightforward as well. Right. So okay. So again, this is Alex's section, so I'm just reading off of his notes here. The Matplotlib also offers some additional ways for graphing zeta using a scatter plot, a histogram, a bar plot, or error bars. So yeah, a lot of them take very, very similar inputs, whether it's just an array of variables, or sometimes you can use more high-end ways of storing data, like pandas data frames too, which we're actually going to get to, pretty soon. And yeah, these the neat part about them, as Alex mentioned in his notes, is that many of them do use very, very similar APIs, as in you can just feed in similar types of data and use similar ways of changing the labels or changing the graphics, and yeah, just use the same core set of principles when running them. So Seaborn gives you a lot of ways of, Seaborn is a package library that gives you a lot of ways of using a lot of neat styling and a lot of fancy tools for graphic visualization that can handle a lot of large sets of data. And Seaborn just generally has a lot of advantages in the sense that a lot of the styling can come pretty automatic, and it gives you a lot more options in terms of what are the types of graphs that you can produce. Like we have a simple line graph, or in this case, this is a sine wave. Just it's just at very, very irregular intervals. So it's not the smooth form of a sine wave you'd normally see. It's very, very erratic, very, very scattered. Um, Although it's just defined using the sine function in NumPy. And with Seaborn, you can set a style using darkgrid, using the style like darkgrid, like this one, to just give you different really, 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 really good built-in color schemes. And Seaborn also has some data sets loaded in specific for brain data, such as the fMRI one. So using one of the built-in data sets, so this is known as the fMRI dataset, comes built in with Seaborn. We can create a line plot specifically using, or specifically in tune with, the variables and labels just present within neuroscientific data itself. So across each time point x for a signal y, we can cover the different signals given from fMRI data. So this would be some sort of measured variable of signal across time series data. So for each point in time, with for two different regions, for maybe the parietal lobes or parietal regions of the brain, and the frontal lobes or frontal regions of the brain too. So just using SNS.lineplot, input data equals fMRI, and label each variable accordingly. Show the plots, and there it is. You can even add a second set of variables using like using the style function or using the style input with events. So this is this just gives you a more elaborate way of demonstrating or visualizing additional responses when measuring fMRI data or similar time series data, like perhaps if you're taking input data from EEG or maybe even DTI as well, diffusion tensor imaging. Some other new data sets that are just available include include data of information or statistics on car crashes. Say if you're measuring how fast people are going versus whether or not they're drinking alcohol or how much alcohol is being consumed, you want to take a look at the prevalence or the observations of car crashes too. So Seaborn has a lot of neat built-in data sets, and using some built-in functions like relplot. So that can give you some ways of plotting a plotting variable using different means too. So this was actually what Alex was showing as well. I wonder if he's going to come back. But celluloid gives ways of producing GIFs too, and animating them as well. I do not have the GIFs in front of me. Let me see if I can run them. Nope. Okay, so I need to run these from the beginning. I need to rerun the notebook. Okay. I'll just run it and see if we can produce the GIFs. So celluloid, I guess while GIFs may not be too common in print publications or in manuscripts, in certain other medias or forums, such as through Twitter or maybe even other places, producing visualizations and GIFs can just be an extremely beneficial way of communicating your research in ways that simple graphics and simple images can't truly capture. Pip install celluloid gives us a way of creating a camera object from a given figure, and by inputting data across it, by inputting data across that figure, we can then take a snap with the camera for the scatter plot at each instance. And I'm not sure if it's saved here or where did Alex save them. Let me look through the files themselves and see if I can show the GIF. Nope, it's not being saved here. But the I wonder if Alex had it saved on his computer and if he was going to show it. I'm just going to read through his notes right here. Create the GIF using the animate method. Okay. Okay, so IPython offers a way of importing, of displaying. Sorry, so IPython offers a way of showing animations in Jupyter using HTML. Oops, shouldn't be animation. Should be. Right. See if you can see this fancy GIF right now. Awesome, that is super cool. So now demonstrating notebooks or sharing visual results in real time. Boom, you can make a GIF right there. And that is super cool. Usually, sometimes notebooks like Jupyter notebooks or Colab research notebooks can be very, very large and clunky, and producing images can just be, a pain. So it's always nice to be able to just show something appearing, and this also just gives you a lot of power and freedom in terms of perhaps maybe not just with this simple sample data, but with time series data that evolves over time. Perhaps you see certain animations and certain GIFs of brain regions that fluctuate with response to being exposed to stimuli, or brain regions, or how how different systems or signals in response to different variables in a network of neurons may respond over time with varying voltages or currents, inputs and outputs. And yeah, just make some really, really cool GIFs, save them, and share them, but not in a Prince publication where you won't be seen. Okay, yeah, the Fourier transform. Okay, so the Fourier transform also gives you a really, really powerful tool of visualizing input data. And I wanted to use it as an example in particular with respect to neuroscience or neuroimaging data. So the Fourier transform, for those of you who maybe aren't so familiar, is the weighted summation of the sinusoidal waves can be used to reproduce the original oscillating signal. I've explained some of the mathematics here, with a function to create the signal. So generating the amplitude of the signal for some given parameters, time steps, number of points, and noise. The equation for the signal is shown here. So you have an exponential variable, or two exponential variables, times a specific amplitude that is evolved in response to parameters themselves, in response to the parameters that are given to the function. And the input signal then can be given an additional noise, alongside some sort of identity matrix I, which is normalized in response to the number of points too. So let's give some variables for amplitude, frequency, and decay, and produce some signals which are being saved right now. So save plot gives you a way of, or this is a function that I've defined right here, using the save fig function from matplotlib. So instead of showing it in the Jupyter notebook, they're saved as files in the folder of which I'm running. So maybe I can share one of them, or perhaps maybe we might be running a bit short on time. Yeah, but these are just saved as PNG files that you can very easily save directly to your computer, instead of having to do like right click save image as, which is not always the most reliable method of saving an image. Okay. We're also going to take advantage of NiLearn. So NiLearn, as described here, gives you a lot of is a very, very high-end like framework or package for visualizing a lot of data in neuroscience, such as brain volumes, as well as performing the appropriate statistical and machine learning processes and methods from the input data. So just as described, you can use it for modeling, classification, decoding, or connectivity analyses themselves. And we're going to load a cortical surface data. So this is a very famous or very, very widely used set of data from Destriou et al., so known as the Destriou parcellation surface, taken from this manuscript. Maybe I can open it up and just show you the manuscript if it's there. It might take a while to load. Okay. My internet can be a bit slow sometimes. So in neuroscience, there's this problem, or maybe there are some issues that can arise frequently when visualizing functional brain imaging data, for a few reasons that I've outlined here, or for a few notes, or for a few tips that are very, very relevant to some of the problems. And it's not loading. For some of the problems, when taking images of brain data, or when measuring regulation or dysregulation of various regions, or comparing different forms of connectivity, such as structural and functional connectivity between different regions, or between different nodes in a network that's being used to model the brain, or model different regions as they function together. So as described here, the resting state data, so the data that's taken when the brain is at rest, can often be noisy when you take similar voxels with the effects of random noise effects. So for those of you who maybe aren't so familiar, resting state data, we often define it as what goes on in the brain when it's at rest or when it's not doing anything, which is also a question or a feature that's up to debate as well. One issue that commonly arises when interpreting the data as described, is that there's a lot of random noise, and we want to. One problem can involve, limiting that noise or trying to get rid of it in the most appropriate way possible. So a second point I mentioned is that the framework, we we want to, sometimes it can be difficult to provide interpretive frameworks. So if you look at a particular network, such as the default mode network, um, we want to have a way of measuring the brain data underlying the images observed, while still, in a way that can be coherent and consistent with other networks, or in a way that can reproduce or really, really tell us what we believe might be significant about that data itself. So we also want to use some strong statistical correlation techniques that might reduce some sort of the issues given by time point errors. And always, as always, just look for very, very simple ways to visualize the data. So I guess just in general, if a lot of the data can be very, very noisy, it can be very tempting in some ways to want to visualize just the data that appears to be nice, that appears to be characteristic or significant. At other times, you want to use some sort of statistical methods or techniques that can reduce or get rid of or absolve the noise without actually harming or without actually reducing the quality of the data itself. So yeah, that gives you a good overview of some problems or issues in parcellations and parcellation techniques. Let's load some of the data. So from Nylearn also has some built-in data sets, such as the DistroU dataset from DistroU et al. So DistroU et al. We can load into this variable DistroU atlas and then take a look at the left hemisphere. So the map. So what's being loaded into the left hemisphere of the DistroU data. Yeah, so fetch surface average. So fs average 5, we're going to name as a variable for the surface template, as described as the PL and inflated version, and so-called depth maps used for shading. And then we just wanted to take a look, or we just, and in these lines we just wanted to print the locations of the files themselves after they've been downloaded. So it looks like for me they downloaded to where Nylearn is being stored. The package Nylearn is being stored in my Conda environment, so in my mini Conda 3 Jupyter Notebook environment. Just be mindful of where data is being stored as well too. And boom, let's take a look. Some regions of interest being plotted for the parcellation scheme itself for the left hemisphere of the brain with a lateral view. So a background map using the background data. So the BG map with some specified darkness value just for the colors themselves. We can visualize the parcellations on the PL surface using Nylearn as described. Yeah. So plot with the plotting variable, we can also use the plot connectome for creating a so after creating a synthetic connectivity matrix, so taking the labels between the left and the right hemispheres, we can create a plot using some input core. So just some x variables giving you the coordinates for the numbers of parcels for the different regions, and the coordinates themselves of the connectivity. Sorry, the coordinates themselves that can be used to define the connectivity matrix. And plot them with some sort of edge threshold and give them a title. So the FS average of the DistroU atlas. Demonstrate what the plots look like. And I wanted to use these examples just to show what Nylearn is really, really capable of with some built-in features for specific sets of data, like specific types of data, showing how simple and easy some of these things can be. In neuroimaging, when a lot of the tools and a lot of the techniques are already existing, and you just have to be able to really, really apply them. Nylearn's plotting function also gives you some ways of creating some interactive surface plots with the parcellation techniques. So why not just be able to visualize the different regions of the brain and give the user some sort of control or of what you're looking at? The back hemispheres, the front, the top, the bottom, left and right. Yeah, and this in Jupyter Notebook, you have to make sure you use the view function for this one for plotting the surface, or for when viewing the surface. So yeah, view surface just gives you a lot of potential for interactive visualizations. Maybe we can even zoom in. I don't know if these actually work. Cool. I downloaded a PNG. I don't know if these actually work for all forms of. Yeah. For all, I think some of these tools might depend maybe on your browser or what operating system you're using. Like right now, I'm actually just dragging using my mouse, using the cursor on my MacBook. Yeah, and all right. So these tools in the top change what exactly your cursor is doing, what you can control. So you can change to zoom mode, you can change to panning, or you can give it a nice little turntable rotation. Oops. Yeah, there we go. Pretty cool. Make some visualizations. Very, very interactive as you go. I'm not going to comment this one, but you can also open it in your browser using view.open in browser. And it looks like we've already done that, the view connectome. Okay, so finally, or for the final half of this, tutorial for this workshop, we'd also want to demonstrate what you can do with matrices with Seaborn. So with some input data given in grid form or given using NumPy's random function to give you a set of random data in two different directions. So 4 data points in the x direction or 4 data points in the first dimension with 6 in the other. Just generate a random set of data between 0 and 1 and plot a heat map accordingly. So this uses just an input array, 2-dimensional or 1-dimensional, I believe. You can give if you specify things a certain way. No. I believe heat map actually does. Actually, no. I think heat map actually does require 2-dimensional data. Plot accordingly. You can remove labels by setting x-tick labels and y-tick labels equal to false, and even change the color bars. So yeah, Seaborn has some really, really cool built-in functionality, and I'm going to skip over this. Just skip over some of this stuff just for the sake of time. I was going into a bit of detail on some mathematics behind some ways of describing connectivity using eigenvectors and eigenvalues as given from some sample data. But I did want to demonstrate in the final 10 minutes a neural network approach to analyzing functional connectivity data for some sample input data for ADHD. So the functional connectivity, as I've described in the notebook, gives you a way of showing using basically a statistical value for correlation of brain activity between regions, how regions connect between one another and make up connections and networks known as the functional connectivity network, essentially describing how they work together. So we want. I'm actually going to demonstrate some neat ways of visualizing. I need to run some of these cells beforehand because these do take a while. Visualizing some of the input data sets of ADHD. So this is some ADHD data set from Du et al. Classifications predictions of brain disorders using functional connectivity. And we are going to use a neural network itself. A neural network, a set of steps using some machine learning technology. So by creating a neural network to visualize some of this data after performing a decomposition on it using independent component analysis. So with the input data, ADHD data, and the num, so the number of participants and the number of subjects, we have a 20-component decomposition. So this eigendecomposition method basically uses the independent component analysis as a way of assessing how much variability there is between control groups and between groups of patients that have ADHD, and seeing if we can truly demonstrate the differences in classifying in classification and figure out if there are specific regions of the brains that are targeted or specific regions of the brains that are involved with ADHD that can be visualized easily, but based on underlying components of based on underlying components being used to draw information from the data itself. So this uses decomposition from NiLearn, and I believe it's from some machine learning package. I can't remember which one. I believe it's scikit-learn. That's right, scikit-learn. Using the input scikit-learn machine learning package, we want to fit the data to a function so we have the ADHD data and give it some sort of function. Use the dot func to give you a way of retrieving components give you a way of modeling a function that can represent the data itself, how it's drawn from the stimuli with corresponding variables underneath. And right now, the reason why this is taking a bit of time is because we're actually fitting a built-in model to the set of data itself and using a specific number of components for the decomposition. For the rest of the lines, we also want to retrieve the components, use a mask to project it into 3D space, so give you an image, which can be shown as soon as this is done loading. It shouldn't take too long, maybe like another minute. And again, just trying to be a bit more hasty because we might be running out of time pretty soon. Yeah, but feel free to ask questions as well. Yeah, so the decomposition method, excuse me. So this data itself, this data itself was collected from some research done on the neural correlates of ADHD. So the original data set, as described, is in Zhu et al. In this manuscript, Frontiers. Let's see if this loads. Frontiers. Oh, there it is. So there's the manuscript in which it's all described. So, I mean, the only thing we really need to know, though, is the difference between the dataset features for controls and treatments. And skipping down a bit further, eventually we're going to use show some heat maps. These are actually using Matplotlib, so we're not actually using Seaborn for this. So I didn't mean to show you how to use Seaborn and then not actually put it in action. But yeah, you can also use imshow for the correlation matrices, which are produced for the correlation matrices. Excuse me, which are produced from the fit transform function from scikit-learn as well. So, right, essentially all we're doing is extracting the functional connectivity coefficients from the data set and classifying whether a given subject is a control or a treatment. So whether they have the disease or whether they don't have the disease. The independent component analysis from NiLearn is used to extract the functional connectivity coefficients. So by looking at the functional connectivity, wonderful. Components between different regions in an independent component analysis. Essentially, we want to ask ourselves the question like, does this help us retrieve or classify control versus treatment groups in a way that's very, very accurate based off of given input data, or there are ways of optimizing these procedures. There's ways of studying them more in depth. This is just really, really interesting, especially in neuroscience and neuroimaging, because instead of relying on the scans themselves, like instead of relying on specific data, like perhaps, like I don't know, like which regions are lighting up, which regions aren't lighting up. We're actually using the methods or the measures of functional connectivity themselves with the statistical techniques built in with scikit-learn. Excuse me, with scikit-learn. That eventually, as soon as this is finished loading, can be visualized. Yeah. So the maps masker with Nifty. So Nifty is also super helpful, built in with NiLearn. Or sorry, NiLearn also uses Nifty files. So that's where the word Nifty comes from, the map masker. So you can standardize it, make sure you detrend. Some of the variables or some of the parameters are a bit self-explanatory, some not so much, like low pass and high pass. Those are some types of filters being used when processing input data from signal processing metrics. The filter gives you a way of basically either detrending or downsampling data as needed, or rather filtering out data. Excuse me, when filter the filters, excuse me, low pass and high pass filters give you a way of getting rid of noise that may be unnecessary and just getting to the form or the function of the data itself, as given or as represented by the nature or the relationship between of how different regions of the brain respond or correspond to each other. With this for loop, we just take a look at, we just want to go through the data itself. So the function data, sorry, using ADHD.func, the func file, the confound file. So looking at the confounds too, and the phenotypic observations. So whether it's ADHD or whether it's a or sorry, like if we have ADHD, so if is ADHD from the phenotypic from the phenotypic from the phenotypic list ADHD, if that is one, then we add it. Then we add it to our list, or we don't. Right. So this one's taking a bit of time because we're actually masking the. Cool. Thanks for the link, BrainHack. Just a few minutes left. Maybe this can be a little homework for the reader if we don't have enough time for it. Feel free to drop any questions. Like even just general questions about visualization, I'd be happy to answer. Okay, so I do have I think I have the notebook run in a I have the notebook run in a different tab. So I'm just going to stop sharing and then share a different tab. Right here. Okay, so this is just the link to the finished results, which I shared the link earlier from GitHub. Correlation metrics by looking for the correlations of connectivity between different regions and seeing if we can fit them accordingly, and stratifying the data using a stratified k-fold. So that just gives you a way of classifying them appropriately, or making sure the classifications line up in a way corresponding to the way we guessed, or the way we might be estimating whether certain sets of data respond to ADHD or respond to control. So the connectivity measure and the connectivity matrices can both be extracted with the corresponding correlation, and boom, we can plot them using the plots, using some heat maps, or using the matrices themselves that have the data, and using plot.imshow. And yeah, it looks like we're just out of time here. But for each subject, we want this is the corresponding connectivity matrix for each subject with ADHD or without ADHD, because there were 40, and I believe it was 20 with and 20 without, if I remember correctly. And finally, I had some links to some other resources. SciPy, Scikit-learn. You want more help with neuroimaging itself? Why not join the NiPi user group? Ask questions on Neurostars. I don't know how active they are so much. Neurostars is very helpful. Neurostars is also Stack Exchange too, for more research-based questions. But yeah, Neurostars is very, very helpful with imaging and with Python visualization, especially within neuroscience and within neuroscience, and especially with neuroimaging. And yeah, Scikit-learn has a mailing list as well. All right. Thank you all.
Thank you so much. I wanted to give you a special thank you for sticking around and taking the lead in the face of fire. Literally.
Yeah, I wonder if Alex is okay. So apparently Jess just messaged on Slack. There was a alarm that went off at
Oh.
But okay, so alarm going off at 2:50 CS. Security and reception said it's for the 7th floor. You don't need to evacuate. I don't know if that's if Alex was, but I hope whatever happened, it's okay.
Yeah. Let's hope. Well, hopefully we'll see him later in the day on other platforms. We also wanted to give a shout out that you're still interested in leading a project, so we'll definitely see you. We'll be seeing you throughout the hack. You'll be on the dashboard.
Yeah. That's what it is, right? Yep.
Yes.
Yep.
Yes. So Hussein will be around for the rest of the week on the Discord server, answering questions, and this whole session will be available in the replay section if you want to go through things a little bit slower or at your own pace. or skip to sections that are interesting to you. So yeah, thank you so much. After the break, or we're going to take lunch now for the next hour, and we'll be back to talk about all things MRI. We'll start with an intro MRI, and then we'll talk about MRI features and BIDS apps and all of these fun things. So we give a digital round of applause to Hussein and Alex. Thank you so much. And I'll give a real one. Yay!
Thanks, Aaron. Thanks, guys.